we are going to continue with our chapter on the universe, and in this section, we'll look a little bit more into the details of stars. So let's look at this video on how a star is born.
Nebulas house baby stars in every spiral arm of the galaxy.
These regions are the nurseries for new stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink.
Stars are made out of gas, basically, and our galaxy has gas. In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk. And it's from this gas that new stars are born.
By observing nebulas at different stages in their evolution, the story of a star's birth begins to emerge. It all starts inside a cold, dark cloud of dust and hydrogen gas, where a quiet tug of war begins. The cloud wants to dissipate like smoke in the air, but gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. Gravity wins, and the material crunches down into a disk that's the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it gets denser and denser and hotter and hotter, until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium, and with a burst of nuclear energy, a star begins to shine.
These stars eventually get their nuclear fires going in the core. And when they do, they heat up. They can expel the material that's around them so that it kind of clears up the neighborhood.
Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns.
It blows away the gas, it blows away the dust, and it lets us see this beautiful new thing, this place where the star has been born.
A human lifetime is too short to witness the wonder of a star's birth in the spiral arms. But by speeding up millions of years of cosmic time into just a few seconds, we can see one star born after another. Here and there are even more brilliant flashes of light, coming from some of the most violent and dangerous neighborhoods in the entire Milky Way galaxy. Here, stars aren't born, they die. Nebula.
Okay, so we see that our stars that we have in our universe all originate from this nebula, which consists of gas and dust, and of course hydrogen. As the gravity overcomes the forces or the pressure forces of the gas to push out, a protostar is formed. And so when the protostar is formed, we have that burst, that nuclear energy that's given off from the fusion reaction that occurs when two hydrogen atoms come together to form a helium atom. And so eventually, as the protostar starts swirling in that disk can get more accumulation of gas, and then you have a star being born. So when it comes to stars, stars are massive, dense balls of incandescent gas. We know that if you look at our sun. The power that the stars have, the energy that we have that keeps this star glowing and producing energy, which for us, we benefit from on Earth, is at the core of the star, as we've seen before, and that is from fusion from two smaller atoms coming together. Our sun is an average star, and it's used as a reference for understanding other stars. And I thought that was interesting for us to look at the scale of the stars relative to us. So this is Earth, and this is the relative size of Earth and the planet Jupiter. If we move along our scale, here is Theta, which is a star, which is just about the size, a little bit bigger than Jupiter. Proxima Centauri, which is one of our close stars next to our sun. And next to that, relative size, which is about 10 to the 6 kilometers, is our sun. Now, our sun is big, but when we compare our sun to Sirius A, it's not quite as big. And this is Pollux. And then we have another big star, Arcturus. And if we keep going, there's our sun back there in small yellow dot now. Because now we have Rigel. And then there's the sun, little yellow dot, Deneb. Pistol. And we see the colors have changed here. And then we go Antares. And then there's Betelgeuse, which you can actually see in the constellation of Orion. Canis Majoris. And so there you have some relative sizes of stars compared to our sun. So our sun is going to have a lifetime. We saw that in order for the stars to be born, we need a nebula. Let's look at the lifetime of the sun.
Like all stars in the universe, the sun is not immortal. The sun was born 4.57 billion years ago. It survives by burning 600 million tons of hydrogen atoms into helium atoms in its core every second. However, there is only a finite amount of hydrogen in the core of the sun. For the next 4 billion years, the sun will continue to fuse hydrogen to make helium. As more helium builds up, the core will shrink. As a result, nuclear fusion reactions accelerate. Faster fusion means more energy output. In 3.5 billion years, the sun will shine 40% brighter than today. At this point, Earth's oceans will boil, and the ice caps will permanently melt. All the moisture in the atmosphere will be lost. Life will not likely survive, and Earth will become brutally hot and dry, like Venus. After that, the situation gets worse. 5.4 billion years from now, the sun will exhaust all the hydrogen in its core. The core will heat up and get extremely dense, but the sun's outer layer will expand a lot. It could expand big enough to swallow Mercury, Venus, and maybe even Earth. Even if it doesn't grow as far as the Earth, high temperatures will completely burn our planet. Once the sun has emptied its fuel reserves, it will become unstable. And as a result, it will begin to pulse. Each pulse will remove more of the sun's mass until all that's left is a cool, dense core. This core is called a white.
dwarf. The sun will spend the rest of its days as a white dwarf, slowly cooling and dimming as time passes. By this point, Earth will be completely inhospitable.
So the sun converts, let's go back. The sun converts
Like all stars in the
about 1.4 times 10 to the 17 kilograms of matter each year. That's a lot of matter within the sun. It was born about 5 billion years ago, and there's enough hydrogen for this reaction to occur for another 5 billion years. The lifetime of the sun or any star depends on the mass. Less massive stars have longer lifetimes, and more massive stars have shorter lifetimes. The brightness of a star is described by its apparent magnitude, which is a scale that compares some of, familiar objects within observable limits to us here on our Earth. And so in this scale, you would see some of those familiar objects. You have, for example, a apparent magnitude of around positive 20 is your naked eye limit with a telescope. Pluto, it's about positive 15. And then, Andromeda Galaxy, let's see, Sirius, which is the brightest star, the apparent magnitude of Sirius, Jupiter, Venus, and then here's the full moon, and that's about 26, which is the apparent magnitude of the sun. So there are differences in stellar brightness, which depends on the amount of light that's produced by the star and the size of the star and the distance that the star is from us, observing it on Earth. So this apparent magnitude was a scheme that was sort of developed to quantify observed brightness. And then there's the absolute magnitude, which is the brightness adjusted to a defined standard distance. So, for example, we're here on Earth and we're looking at the star that's a certain distance away. What we will see based on that distance is an apparent magnitude of 3. When we're talking about the absolute magnitude, we're talking about the brightness of the star at a fixed distance, and that's 10 parsecs. And so we will compare the brightness of all objects, relative brightness of all objects, at a distance of 10 parsecs. And so we start looking at the total energy that's radiated per second, which affects that brightness. And so luminosity of the sun, for example, is given 1 solar luminosity. Now the stars, as we saw, the stars have different colors, and the different colors are sort of associated with different temperatures. So a yellow sun, here's a temperature of about 6,000 Kelvin. We saw smaller red and orange stars. And then the blue-white star, which would be about 10,000 Kelvin. And we saw also the star Rigel, which had a temperature of about 25,000. So our color variations go from red, yellow, bluish white, and all of those color variations are related to surface temperature. You see some colors here, and these are indicating sort of the surface temperature based on that black body radiation curve. And so we get an idea of what the temperature of those stars are based on their black body radiation. Now, stars are classified into a scheme which is based on temperature from the hottest to the coldest. So it goes from blue to red when it comes from hottest to coldest. And in that classification, we have 7 spectral classes: class O, B, A, F, G, M, F, G, K, and M. And those corresponds again to different temperatures that the stars would have, with the hottest being the first and the coolest or coldest star being the last star on the list. All right, so we will stop here and then come back in Unit 3 when we take some more notes about stars.